just as normal subgroups are the important class of subgroups in group theory because they allow you to construct factor groups, ideals are the special subrings of rings because they allow you to form factor rings. So we're going to study that today, look at how we construct factor rings, when they're defined, and how the various properties of the ideals that are used to define them affect the properties of the factor ring that we get out of it. Recall, first of all, we're going to use the following result from group theory quite regularly here, is that if S is a subring of R, in particular if S is an ideal, then the cosets x plus s and y plus s are equal if and only if x minus y is an element of S. And in particular, this means that x plus s equals S if and only if X belongs to S. And so we're going to be using this quite regularly throughout this section. So when we go to try to define a ring structure on the factor group R mod S, addition works just fine. Remember that all rings are abelian groups under addition, and therefore any subgroup of them, in particular any subring, is therefore a normal subgroup, which means we can always construct the factor group R mod S for any subring S. However, where we might run into trouble is in defining the multiplication. So addition has no problems in this set. We still have that this is an additive group, but then when we want to go and define the multiplication, we run into an issue. Now, the way that we would want to define the multiplication inside this factor group, this set of cosets, is the following way. We would want to define it as A plus S times B plus S is equal to AB plus S. We would like to be able to just multiply in the factor group by multiplying the elements that represent the various cosets. The problem is that this is not well defined if S is not an ideal. And that's going to be the concept behind Theorem 101. So this is not well defined if S is not an ideal. So let's look at Theorem 101. So we have let R be a ring and S a subring of R. The set R mod S, which is defined to be the set of cosets R plus S, where little r comes from R, is a ring under the operations x plus s plus y plus s equals x plus y plus s, and x plus s times y plus s equals xy plus s if and only if S is an ideal of R. Not just a subring, but an ideal. So let's check the proof. So let's suppose that S is an ideal. we're going to show that if S is an ideal of R, then this set R mod S with these operations does in fact form a ring. Now there are lots of things that we have to check about this. We need to check that addition on this set forms an abelian group. That part's going to be easy. Since S is a normal subgroup, a normal, I should say additive subgroup of R, we have that R mod S is an additive, that is abelian group. All right, so that takes care of 3 of the conditions for being a ring. Now, we have 2 other conditions. We need to show that multiplication is associative and that it distributes over addition. But before that, we've actually got something even more important, sort of a zeroth condition, and that's to show that the multiplication we've defined is an operation on this set. In particular, we need to show that it's well defined. Okay, we show that multiplication on R mod S is well defined, based on the assumption that S is an ideal. So let's suppose that we have a coset X plus S, and it's the same as the coset X prime plus S. So we have both X and X prime, which are representatives of this single coset. And we also have that Y plus S is equal to Y prime plus S. Now, because of these things and the note that we mentioned before, this means that X minus X prime belongs to S and Y minus Y prime belongs to S. And we wish to show that no matter what representatives you choose, if I choose X and Y and apply them to this formula, we'll get XY plus S. And if we use X prime and Y prime, we'll get X prime Y prime plus S. We want to show that we get the same thing, that the precise representatives we choose for the cosets don't change the output of the multiplication. If they did, then we would not have a well-defined operation. We'd have an operation which depends on the way that you wrote down one of the elements of this set and not just the element itself. So we want to show that these 2 cosets are equal under the assumptions that we've made. Now we have the following. We can do what we want by proving that the difference between the 2 representatives belong to the set S. Now, a common trick that we use in algebra in situations like this is adding and subtracting the same thing. So xy minus x prime y prime is equal to xy minus x prime y plus x prime y minus x prime y prime. A way of thinking about what's going on is that we are trying to basically bridge the gap between the element xy and the element x prime y prime. And currently, they're very different from one another. We've got 2 factors which aren't related to each other, to the 2 factors on the other side. However, by adding and subtracting a term which includes an element from the first term that we started with and an element from the second term that we started with, we can create a situation where we can use some of the ring facts. In particular, we can use distribution. So when we have xy minus x prime y, that's the same as x minus x prime times y. And here, x prime y minus x prime y prime is the same as x prime times y minus y prime. Now, we know that x minus x prime belongs to S, and y minus y prime belongs to S. And furthermore, we know S is an ideal. So since S is an ideal, x minus x prime times y belongs to S, and x prime times y minus y prime belongs to S. Hence, since S is just a subring, it's closed under addition, hence x minus x prime y plus x prime y minus y prime belongs to S, but that was equal to xy minus x prime y prime in the first place, so that belongs to S, which means that xy plus S equals x prime y prime plus S. So that means that multiplication in R mod S is at least well defined. Now, proving that the multiplication in R mod S is associative and distributive over addition is a straightforward exercise that is just based on the fact that multiplication in the original ring R is associative and distributes over addition, and the fact that multiplication in the factor ring is basically the same as multiplication in the original ring, or is defined in that way. You can find details of these two steps in the notes. We're going to leave that for now, so we have the one direction. If S is an ideal, then R mod S is a ring under the natural definitions of operations in it. So let's go the other direction. So let's suppose that S is not an ideal. Now, if S is not an ideal, then that means that it must be either not a left ideal or not a right ideal. The arguments for these two cases are pretty much completely symmetric, so we're just going to do one of them. So suppose S is not a left ideal. And we're going to show that multiplication in R mod S is not well defined, which will finish up the if and only if statement in the theorem. Now, if S is not a left ideal, that means that it's either not an additive subgroup or it doesn't satisfy the multiplication condition. We know that it has to be an additive subgroup of R. It has to be a subring of R. So that's not going to be what the problem is. So we can say instead that we can let let little r be an R, let little x be an S, such that Rx does not belong to S. This is guaranteed if S, the existence of such elements are guaranteed if S is not a left ideal. So now we have that R plus S times x plus s, using the multiplication definition that we had above, is equal to Rx plus s, which in particular, notice, is not equal to s, since Rx does not belong to s. But if we take 0 plus s times x plus s, this will give us 0x plus s, and 0 times x is just 0. And so 0 times x plus s is equal to s. However, since sorry, I got this backwards. We want to leave the r over here, but 0 in the second component. We want r times 0. Which is s. What I wrote down before is not incorrect, but it's not useful. This is useful because we note that x plus s is equal to 0 plus s. And we know that because x belongs to s as part of our assumption. Well, this means that we've got uh, a multiplication of two things, and the first elements are equal, and the second elements are equal. They're just written a different way, but their products are unequal. That's an ill-defined operation. Multiplication doesn't work in this case. So in this case, multiplication is not well defined. So what this tells us is that ideals are precisely the only type of subrings that will work to define a factor ring. So ideals are exactly what we want to do here. Now, describing rings as factor rings is incredibly important in ring theory. We will be constructing rings using factor rings and describing rings as factor rings all the time. So let's see some examples. So let's let our original ring be the integers and the ideal I be the set of multiples of n for some integer n. For the sake of this, we'll say that n is greater than or equal to 2. This doesn't have to be the case. Well, let's do n is greater than or equal to 0. Will work. Now we have, do need n is greater than or equal to 1 for part of what I'm about to do. We know that I is an ideal. We've already seen this. So let's look at what the factor group R mod I looks like. Now, by definition, it's going to be the set of all the cosets of the ideal I, which we write as nz. Now, we can start writing out some of these cosets. We've got the coset with representative 0, the coset with representative 1, coset with representative 2, or plus nz, etc., etc. We've got the coset with representative n minus 1. But then notice that we can stop here, because if we went one more space along, we'd have n plus nz, and n, whatever number this is, belongs to nz. So that is the same as 0 plus nz. And then the next one, n plus 1 plus nz, would be equal to 1 plus nz. And that's because belonging to the same coset of I is exactly the same as being congruent modulo n. This is going all the way back to the beginning of the previous course, when we were looking at congruence modulo n. And so what we see here is that the ring that we get out of this is precisely the same ring that we've been looking at a bunch of times. Now we've usually written it as z mod nz, and written it as like 0 bar, 1 bar, 2 bar, up through n minus 1 bar. But this notation that we've got, this idea of factor rings, is what justifies this notation here. We already saw last semester that this notation is justified because this group really is isomorphic to the factor group z mod nz, and indeed it's also the same as the factor ring z mod nz when we consider them as rings. Now, a couple notes about factor rings. Factor rings share some of the same properties that the original ring does, but not all of them. So let's let R be a ring, I an ideal of R, and you're going to have a couple of exercises which ask you to show that if R is, for instance, commutative, then R mod I is also commutative. Also, if R has unity, then R mod I has unity. And this works for any ring and any ideal. Now, one might expect that we could go further. So if R is a domain, one might hope that R mod I would necessarily be a domain, but that is not true. R mod I may or may not be a domain. And we can see that in from the previous example. The ring Z, the set of integers, is a domain. However, the rings Z mod NZ are not necessarily domains. They're only domains when n is a prime number. So this shows us that not all nice properties descend, but some do. And these two, commutativity and unity, are very, very important. The other thing that we're going to note based on this example is that before we had been using this overline to represent equivalence classes, and then later cosets, which are equivalence classes. We're going to continue to do the same here. So when R and I are understood, we may use the notation x bar to stand for x plus I, to stand for the coset of I with x as its representative. Now, we will sometimes use the bar and we sometimes won't. It's sometimes helpful for us to leave it in. To leave in the plus I and instead of using the bar. We'll switch back and forth freely between the notations when R and I are understood. However, if you're quotienting with respect to, say, two different ideals, if you're creating two different factor rings with two different ideals, you don't want to use the overline notation. You want to write it out explicitly as the cosets of the particular ideals you're working with. All right, let's look at another example. So let's let R be the set of polynomials in the variable x with real coefficients, and I be the ideal generated by x squared. Now, the ideal generated by x squared is the set of all multiples of x squared by elements of R. By elements of R here being this whole set of polynomials. Now, this means that the ideal I contains lots and lots of elements, all the things that you could get by taking a polynomial and multiplying it by x squared. So in particular, I consists of all polynomials where all terms of the polynomial have degree at least 2, plus the element 0. And we already looked at this as, or something like this as, an example of an ideal back when we were talking about ideals. Okay, now one thing that we may do is we may interpret R mod I as being like R, but all elements of I are set to 0. So one way of thinking about the factor rings is that we're starting with a ring and then we're declaring, all right, this set of objects we're going to just consider to be 0. We're going to collapse it down. And in particular, that set of elements has to have the form of an ideal. And when we do that, that is the process of going to a factor group. Anything that was in I before now becomes 0 in the factor ring R mod I. And so intuitively, that's a lot of what's going on. And that intuition can carry us quite a way in terms of understanding what's going on. In this factor ring R mod I, it's going to behave sort of like the ring R, the original ring R, but anything that has degree 2 or greater is just going to go to 0. It's just going to be eliminated. So, let's see how this works. So, for example, let's take the product 2 plus 3x times negative 4 plus 5x in R mod I. So I'm specifying R mod I here so that I can use the bars instead of writing plus I again and again. Now, we just proved that this factoring works when you define the product of two things in the factoring as being the equivalence class of their product. So, to find the product in here, we can just take the product of the two representatives. If we take the product of the two representatives, we get negative 8 minus 2x plus 15x squared. And this is correct, but let's look a little closer at what's going on. Let's switch back to the plus I notation. So plus the ideal I. Now, you'll notice that this 15x squared term belongs to I. I is the ideal generated by x squared. So in particular, it contains every multiple of x squared, and 15x squared is certainly one of them. Now, this 15x squared can essentially be absorbed into I, with the result being that we write this as negative 8 minus 2x plus I, which equals negative 8 minus 2x bar. Now let me break that up, let me write this out a little bit more precisely once. We won't write down this part that I'm about to very often. But if we have negative 8 minus 2x plus 15x squared, all plus I, we can write that as negative 8 minus 2x plus I plus 15x squared plus I. But 15x squared is an element of the ideal I, which means that the coset with representative 15x squared is the same as the coset with representative 0. And the 0 element of the factor group is precisely the coset of the ideal with representative 0. So this is the details of what we're doing. We're not going to run through that pretty much ever again. Whenever we've got a representative of a coset and one of the pieces of that coset belongs to I, belongs to the ideal, we can just eliminate it. We can just throw it out. Now this works really well when an element shows up as a multiple of x squared, but for more complicated situations, it gets a little bit hairier to write this out in full detail. but a lot of our intuition will still be correct. Now notice that in particular this means that we can write out the elements of R mod I very precisely. Notice that any term with a degree of 2 or greater will be an element of I, which means it can just get absorbed into I, like this one was. These two elements together just get absorbed into I. And so in particular, this means that we can describe the elements of R mod I as being A plus BX plus I, where A and B belong to the real numbers. So every element of R mod I can be written using a representative, which is just a linear, at most, polynomial. A polynomial of degree, at most, 1. All right, let's do another example with the with this. But before we do that, let's think some more about what's going on here. So the intuition that we use, especially when we're working with a principal ideal like this one, is the following. Let R be a ring, A an element of R, and let's let I be the ideal generated by A. Now, R mod I is like R, but with A being set to 0. It's like we've decided, all right, anything that's a multiple of A, you're just going to be 0. We're going to collapse everything down, and in particular, that means that in addition, for any x in R, we have that the equivalence class of x is equal to the equivalence class of x plus a, or indeed the equivalence class of x plus RA for any little r in R. And that's because A is essentially being set to 0 intuitively when you move from the ring to the factor ring R mod I, where I is the principal ideal generated by A. A common subset of this example is where we let I be given by a single element. It's still a principal ideal, but that principal ideal is made up of several terms. So in this case, R mod I is like R, but with B plus C equals 0, or in other words, or I should say the equivalence class of B plus C is equal to the equivalence class of 0, which means that the equivalence class of B is equal to the equivalence class of negative C. What this means is that in R mod I, B can be replaced with negative C. Let's see how this works in the next example, which uses the same ring R as the last one, but with a different ideal. Let's let R be the set of polynomials in the variable x with real coefficients, and let's let J be the ideal generated by the polynomial x cubed minus 4x plus 1. Now, in R mod J, we have that x cubed minus 4x plus 1 equals 0, because x cubed minus 4x plus 1 equals J, or is in J. So in particular, this means that the equivalence class of x cubed is equal to the equivalence class of 4x minus 1. And that means that anytime we see x cubed in the ring R mod J, we can replace it with a 4x minus 1. Thus, given any element f bar, which will be a0 plus a1x plus a2x squared, etc., plus an x to the n bar, we can replace, I should specify this is in R mod j. We can replace any term ai xi with I at least 3 with ai xi minus 3 times x cubed, which are, I should put bars over these, with ai x to the I minus 3, and now x cubed becomes 4x minus 1, because we're working in R mod j, which gives ai x to the I minus 2, or 4ai x to the I minus 2, minus ai x to the I minus 3. In particular, notice that we changed an element with degree at least 3 into a sum of terms of lower degree. So we started with an element of degree I, we wound up with a sum of terms of degree I minus 2 and I minus 3. We can repeat this process. We can repeat this process over and over again, starting with with any polynomial, and then any term that has degree at least 3, we can use the equivalence x cubed equals 4x minus 1 in this factor ring to keep dropping the degree over and over and over and over again, and we can keep doing that as long as we have a term of degree at least 3. We can repeat the process until f has no terms of degree greater than or equal to 3. And we can do this with any element that we started with in R mod j. So that means that R mod j can be represented using only polynomials of degree 2 or less. So R mod j is represented by elements of degree 2 or less. I'll write that as plus j, where a, b, and c belong to real numbers. One of the things that you'll notice that these quotient rings do is they make the ring that we're actually looking at easier to understand. In both the examples that we've seen, we started with the ring R, which contains all polynomials with real coefficients in the variable x, and we got it down to a point where we could represent every element of the factor ring using polynomials of small degree. And this is typically what happens when we look at factor rings. Just like factor groups, factor rings are typically simpler than the rings that we started with in some ways. However, they will also be less useful often in other ways, depending on the properties of the ideals I and j. Because we're dealing with both multiplication and addition here, there's a lot more structure, there's a lot more texture to what's going on with factor rings than there are with arbitrary factor groups. Now, in particular, this means that we can look at properties of the ideals that we're looking at and try to say, well, what will they do to the factor rings that we make when we create a factor ring using that ideal? So, to that end, we have our next definition, which give the two big types of ideals that we're going to be that we talk about most often. So of all the subrings that we have, some of them are ideals, and those are the ones that we want to look at because they can create factor rings. However, not all ideals are created equal, and some of those ideals are going to be special. So let's let R be a ring, and I an ideal of R. So there are two definitions we're going to do here. The ideal I is called a prime ideal, or just prime. If I is not R, we don't consider the whole ring a prime ideal. And whenever A and B belong to R, and AB, the product, belongs to I, we must have that either A is in I or B is in I. So so whenever I've got two elements of my ring and I multiply them together and I land in the ideal, I want it to be the case that either A is in I or B is in I. If that happens every single time you multiply two things together that land in I, then the ring I is called a prime ideal. Now, equivalently, we can describe this in the following way, which is sometimes an easier way to prove things, which we'll see in a second. Equivalently, an ideal I is a prime ideal if it's not equal to the whole ring, and if the following condition holds. If A and B do not belong to I, then the product AB does not belong to I. This is just the contrapositive statement of the one above, completely logically equivalent, but sometimes easier to use in proofs. So this is a prime ideal. Its definition is connected to the notion of prime number. Again, we'll see that in a second. However, it doesn't use quite the same a definition that quite matches up with what we are used to. However, this turns out to be the correct one to use in the general ring setting. All right, so then number two, the ideal I is called a maximal ideal, or just maximal, if I is not equal to R and there exists no ideal J such that I is strictly contained in J, which is strictly contained in R. In other words, there exists no ideal between I and R. So I is maximal, meaning there's nothing bigger than it, other than the whole ring itself. This has another equivalent. Equivalently, if J is an ideal, and I is contained in J, then I equals J, or I equal or J equals the ring. There's no room in between the ideal I and the whole ring R for another ideal. So these are the two big types of ideals that we're going to be talking about: prime ideals and maximal ideals. At first glance, it's not at all obvious that there should be any relationship between them. However, it turns out that there is a strong one, which we're not going to state yet until we prove a couple theorems about ideals with these properties. Let's look at a couple of examples of prime and maximal ideals. In the ring Z, the ideal NZ is prime, or let me be more specific, is a prime ideal if and only if n is a prime number or n equals 0. This is an exercise, and this is really using the properties of prime numbers in the integers, and it also illustrates why we use the term prime ideal. Prime ideals were originally constructed to essentially be the correct generalization of prime numbers to arbitrary rings. Much of the early work in rings was based around taking facts about the integers, which were of course very well known by that point, and expanding them to more arbitrary rings. And so the concept of a prime ideal was constructed to generalize the notion of a prime number, hence this relationship here. It's interesting, the number 0 is not typically considered a prime number when you learn about prime numbers, say in elementary school through high school. However, I think that there's a reasonable argument to be made that we should consider 0 a prime number. This is part of the reason why, and we might be able to get more into that idea at a later point. I'm certainly happy to discuss that with anyone who wishes to. All right, let's look at another example of using these terms. If R is a commutative ring with identity, then R is a domain if and only if the 0 ideal is a prime ideal. Now this is pretty much just unwinding the definitions. What does it mean for an ideal to be a prime ideal, and what does it mean for the ring R to be a domain, given that it's a commutative ring with identity? And it turns out that the definitions are pretty much exactly the same. Let's look at another one. So let's let R be the ring Z, and let's show that the ideal I equals 2Z is maximal. Now, there are several ways of showing that an ideal is maximal. We'll see a few of them later. But one thing that we do a lot is we try to construct an ideal that is a little bit bigger than the ideal that we're starting with, and show that the new ideal has to be the whole ring. No matter how we expand things, if we go even a little bit bigger than the ideal I, then we have to get all the way to the ring R, to the whole ring itself. So let's suppose that J is an ideal that I is contained in J, rather, but I is not equal to J. And once we have this, to show that I is maximal, we have to show that J is necessarily the whole ring itself. So, because I is contained in J but is not equal to J, then that means that we can find some element that's in J but not in I. Now, since I contains all the even numbers, X is odd. I has all the even ones, which means anything that's not an I has to be odd. Hence, X plus 1 is even, and therefore it belongs to I, but I is contained in J. So both X and X plus 1 lie in J. But since J is an ideal, it's closed under subtraction, which means that 1, which can be written as X plus 1 minus X, belongs to J. So X plus 1 and X are both elements of J, and therefore their difference is also an element of J. But this shows that 1, the multiplicative identity of R, belongs to J. Hence, J equals R. This is an exercise on your homework that shows that if an ideal contains any unit at all, including the element 1, then that ideal is equal to the whole ring. So we've shown that if J is any ideal that properly contains I, then it has to be equal to the whole ring. And that is enough to show that I is maximal. Okay, so we've got these properties of ideals. The thing that we want to look at is to say what happens when we take factor rings of these ideals. And that's what's given in Theorems 103 and 104. So Theorem 103 says, let R be a commutative ring with identity and I an ideal of R. Then the ring R mod I, the factor ring R mod I, is a domain if and only if I is a prime ideal. So this says that if we start with a prime ideal and form the factor ring, then we get a domain. More than that, it says that if we form the factor ring with any ideal and we get a domain out of it, then the ideal we started with is prime. Many authors actually take this to be the definition of a prime ideal. It's an ideal where when you form the factor ring with it, you get a domain. And then prove what we used as the definition as a theorem in it. Both ways are fine. I prefer the way that we've done it, but it's important to realize that whenever someone says we've got a prime ideal, there are two things that means that are completely equivalent. One is the multiplication property that we use to define it, and the second one is that the quotient ring formed with the ring in that ideal is a domain. So this is a very, very important theorem. And let's see the proof. So let's suppose, first of all, that R mod I is a domain. And let's prove that I is a prime ideal. And I'm going to use the equivalently definition of it, form of the definition of it. So let's suppose A and B are in the ring R, but they are not in the ideal I. This means that A plus I and B plus I are not equal to 0 in the ring R mod I. Since R mod I is a domain, this means that 0 plus I is not equal to A plus I times B plus I, which, by definition, is AB plus I. Now, since AB plus I is not equal to 0 plus I, our conclusion is that AB is not in I. So, what we've proven is that if we start with two elements that don't belong to I, and we multiply them together, we are still not in I. We can't possibly land in I. So, hence, I is a prime ideal. All right, so that proves one direction. That proves that if we quotient by an ideal and we get a domain, then that ideal was prime to begin with. Now let's go the other way. So now let's suppose that I is prime. And we're trying to show that R mod I is a domain. Let's let A and B belong to A plus I, B plus I. B plus I belong to R mod I. Now, notice that in particular this means that A and B belong to R. Let's let A and B belong to R. R plus R mod I with 0 plus I being equal to A plus I times B plus I. Let's suppose that we have two things in R mod I that multiply together to be 0. And so we have that AB plus I equals 0 plus I. Hence, since AB plus I equals 0 plus I, we have that AB belongs to I. Since I is prime, A is contained in I or B is contained in I. Thus, this tells us that A plus I is equal to 0 plus I, or B plus I is equal to 0 plus I. So that gives one of the conditions for being a domain. We've proven that in the ring R mod I, if two elements multiply together, then one of those elements had to be 0 to begin with. So the other things that we have to check is that R mod I is a commutative ring with identity. However, notice that we assumed that R was a commutative ring with an identity to begin with, and so the fact that R mod I is a commutative ring with identity is an exercise. The same exercise I mentioned before. All right, so that finishes that up. We have that a ring is a domain, or the ring R mod I is a domain if and only if I is a prime ideal. Okay, so let's go to what happens with maximal ideals. So Theorem 104 says, let R be a commutative ring with identity, and let's let I be an ideal of R. Now the ring R mod I is a field if and only if I is a maximal ideal. So Theorem 103 showed that prime ideals correspond to domains And Theorem 104 says that maximal ideals correspond to fields. That is assuming that the ring that we start with is a commutative ring with identity. So let's look at the proof. Let's first of all suppose that R mod I is a field. We want to show that I is a maximal ideal, which means we want to show that there's no ideal in between the ideal I and the whole ring R. So let's let J be an ideal of R such that I is strictly contained in J. So I is contained in J, but is not equal to J. And let's let A belong to J, but not I. We're going to try to show that J has to be equal to the whole ring, and that will show that I is maximal. Since A is not contained in I, we have that A plus I is not equal to 0 plus I in the ring R mod I. Now, since R mod I is a field, there exists a B plus I in the ring R mod I such that 1 plus I is equal to A plus I times B plus I. Since R mod I is a field, that means that every non-zero element is a unit, meaning that given any non-zero element, such as A plus I, there's some other element, B plus I, so that when they multiply, they give the multiplicative identity. Now, again, it's an exercise to show that the multiplicative identity of the factor ring R mod I is just 1 plus I, where 1 is the is unity for R. So we get 1 plus I is equal to AB plus I. So that means that AB minus 1 is contained in I. But we have that I is contained in J. So AB minus 1 is contained in J. So that means that AB plus J is equal to 1 plus J. However, since A belongs to J, and J is an ideal, that means that A times B belongs to J. And so we have that 1 plus J is equal to AB plus J, which is equal to just J. Hence, 1 belongs to J, and so J is the whole ring. By that exercise I mentioned earlier, that when a ring contains or when an ideal rather contains a unit, then it is the whole ring. Okay, so that shows that if R mod I is a field, then I is a maximal ideal. Okay, so let's go to Theorem 105. The second part of Theorem 104. So let's suppose that I is a maximal ideal. We want to show that R mod I is a field. So the fact that R mod I is commutative and with unity is an exercise. And so the only thing that we have left to show is that every non-zero element of R mod I is a unit. So let's let A plus I be an element of R mod I be a non-zero element. So that means in particular that A belongs to the ring R, but not to the ideal I, because if A belonged to I, then A plus I would just be I, which is the 0 element inside the ring R mod I. So now let's let the element, or the ideal J, be the sum of the ideals I and the principal ideal generated by A. So now J is an ideal. We have that I is contained in J because J is I plus all of the elements of the ideal generated by A, and 0 lies in this ideal generated by A. So in particular, J contains all the elements of I, but it also contains A. So that means that I is a subset of J, but it's a proper subset of J because J contains A and A doesn't belong to I. Well, now since I is maximal, that means that J has to be the whole ring. So in particular, that means that the element 1 has to belong to J, which remember is equal to I plus the ideal generated by A. That means there exist an element X inside I and an element Y in the ideal generated by A such that 1 is equal to X plus Y. Now, since Y belongs to the ideal generated by A, we have that Y is equal to AB for some B in R. All of the elements of the ideal generated by A look like A times B for some ring element B. Therefore, we have that AB minus 1 is equal to X, or is equal to Y minus 1, which is equal to X, or, it's equal to negative X, and negative X belongs to I. Well, that means that AB minus 1 belongs to I, so therefore, AB plus I is equal to 1 plus I. So, in particular, that means that A plus I times B plus I is equal to 1 plus I. And that finishes things up, because that means that A plus I is a unit in R mod I. We started with any non-zero element of R mod I, and therefore R mod I is a field. So, if we're working with commutative rings with identity, then an ideal is prime if and only if its factor group, or its factor ring rather, is a domain, and an ideal is maximal if and only if its factor ring is a field. Now we have a corollary based on these. We already know about some relationships between domains and fields. So we have corollary 105. If R is a commutative ring with identity, and I is a maximal ideal, of R, then I is a prime ideal. The proof of this is an exercise. And it's really just a combination of theorems 103, 104, and a theorem from an earlier section which relates domains and fields together. So this means that in a common scenario we're dealing with, commutative rings with unity, maximal ideals are a subset of prime ideals. Every maximal ideal is a prime ideal. Maximal ideals are very, very special. They sit very close to the whole ring itself, and prime ideals can be of all different sizes. Now, there are going to be lots of prime ideals which are not maximal. So these two classes of ideals are definitely not the same, not even close, but they do have the relationship that all maximal ideals are prime ideals. Now, I should say that rings in which they are the same, which every prime ideal is a maximal ideal, are an interesting class of rings themselves, but they're really rather special, and so we won't be looking too much at that class of ring. Most of the rings that we look at, if they are commutative with identity, they will have maximal ideals, and then they will have prime ideals, but the class of prime ideals will be bigger.